All right. So with work energy theorem here, guys, work is a change in energy. Okay, that's the big thing we got to remember. Work's a change in energy, but we got to not only remember that, we got to be able to see how that kind of works and where it applies. If I push something up a ramp, why am I doing work? Right. I'm changing its potential energy. If I'm pushing it at a constant speed, I'm changing its energy. If I'm its potential energy. If I'm accelerating it up a ramp, I'm not only changing its potential, I'm also changing its kinetic. Okay. So in either case, there's a change in mechanical energy going on. All right. Now, if I know the force that I'm exerting and I know how long the ramp is, 25 meters, I should be able to figure out the work done. Agreed? Okay. So if I assume that I started at the bottom of the ramp, should I be able to figure out how much the energy changed by? Yeah, in fact, I already did when I multiplied force times distance. Okay, so that's what we got to recognize here is what kind of energy is changing. Okay, work's the change in potential energy this time. Okay, work is force times distance. Okay, change in potential energy means m times g times h final minus m times g times h initial. If I started at the bottom of the ramp, what was my initial height? 0. So what's m times g times hi? 0. All right, so I can get rid of that. Okay, and this question simplifies down to FD equals mghf. All right, so I'm looking for the final height, okay, the height of the ramp. Well, how do I get hf by itself? Divide both sides by mg. Alright, so FD over mg will give me hf. So we have our 150 newtons, okay, times 25 meters, okay, divided by the 55 kilograms worth of mass multiplied by 9.81. Okay, and remember, you need to do top and bottom, right? If you just punch it in, it'll do it from left to right, which isn't the same thing. Right, so. Oh, I had that working this morning. So much for that idea. Okay. Do it the old-fashioned way. So we got 150, okay, times 25, okay, divided by 55 times 9.81. All right, so we got 6.95 meters. I have no idea why it says 10.9. Huh, that would be why. I just went by this because it was the one I could see. All right, we'll change that. 35. That'll come out to 10.9 because I'm dividing by a smaller number. Okay, so 10.9 meters, okay, will be the final height, okay, or the height of the ramp. Okay, is this ringing a bell? All right. Has everybody got that one written down? Okay, write this one down and try it. This is the correct answer, okay, so you'll know if you did it right after you're done trying it. Okay, then we'll go through it together here in a couple minutes. Okay, so in this one, what kind of energy is changing? Kinetic energy is changing, right? Because how do we know that? Well, it's asking about speed. Okay, as soon as it's asking about speed, we know it's got to do with kinetic energy because that's the one that has to do with speed. All right, so we again have that work is a change in energy. Now, when a pitcher is getting ready to pitch, how fast is the ball moving? 0. He's just holding it, right? It's not, when he gets into his windup, even it's not moving. Okay, so it's not until he starts exerting that force on it, okay, through the throwing action, okay, that it starts to change its kinetic energy. Now, we again know that work is force times distance, okay, and that since we're dealing with kinetic energy this time, we're looking at 1/2 mvf squared minus 1/2 mvi squared. Okay, ef minus ei. Everyone with me so far? Okay, since its initial velocity is 0, it doesn't have any kinetic energy initially. All right, so can I solve now for VF? Yeah. Now the trick to this here, guys, is that VF is squared. Right, so first I'm going to move the 1/2 and the m by dividing them. Okay, because if you want to move something, you do the opposite. Now if I want to get VF, I need to square root both sides. Okay, that's what I've done there. So VF will equal, okay, the square root of 300 newtons, okay, times 2.2 meters divided by 1/2 times 0.250, and that should give us 72.7 meters per second. Okay. We're starting to feel a little more confident with this stuff? Yes? No? Okay. Alright. I want you guys to try this one. Okay, I know we're going through a lot of examples, but like I say, this is the most important concept, and quite frankly, I've been playing around with your unit exam, and right now, there seems to be a lot more marks on this than anything else. Alright? Okay, so this one's not a whole lot different than the ones we've been doing. Okay, it's still work energy theorem. What kind of energy is changing here? Kinetic, because I'm slowing down now from 20 meters per second to 0, right? I want to stop. Or sorry, to 6 meters per second, sorry. Okay, so I'm slowing down from 20 to 6. Well, right, so I'm still going to say here that work equals the change in energy. It's just now I'm going to have an initial and a final, right? Whereas before we were always canceling one off. Doesn't really change what we do. Okay, work is still force times distance. Okay, and the change in kinetic energy is still 1/2 mvf squared minus 1/2 mvi squared. Okay, do I have all those numbers? Yeah, everything except d. Right. So if I want to get d by itself, what do I do with f? Divide both sides by it. Okay, so now all I got to do is plug in my numbers. All right, so the car was 1,700 kilograms, right? 1/2 times 1,700 times 6 squared minus 1/2 times 1,700 times 20 squared. Okay, divided by the force, which was 10,000 newtons. Okay, is it okay that this comes out to a negative number? Yeah, it's fine. Okay. We did negative work. The car lost energy. Okay, so it's okay if the number comes out negative. All right. So we're looking, 30.9 meters, right? For that one. You can, but it only asked how far did it travel, and how far is a vector or scalar quantity? Is scalar, right? That's distance. And when we're dealing with energy, energy is also scalar. Work can be positive or negative, oddly enough, okay? But energy is scalar, right? Work, in fact, is also scalar. The positive and negative just has to do with whether the work is done on you or on something else, okay? So if I do work on something else, from my point of view, that work is negative because I've lost energy. From the other thing's point of view, it's positive because it's gained energy, right? It doesn't make it a vector quantity. Right? And since this is distance, okay, right here, that can't really be a negative number either. Right? So if you put negative on a test, I wouldn't mark it wrong. Okay? You still did the question right. Okay? It would be a matter of perspective. Okay. All right. I think we got one last one here, guys. Okay, try that one. All right. So let's have a look at this one. If I use a slingshot, when I pull it back, what have I done? When I pull back a slingshot, what have I done? I've created potential energy because I've done work. I've exerted a force, I've pulled, okay, through a distance, just like you did yesterday in the work lab. Okay, essentially what you did was a slingshot, except you hopefully never let go of the spring scale. Okay, so that it didn't fly off. Right? But essentially that's what you were doing. You were doing work which put, okay, potential energy into the rubber band. So I've got a force of 1,500 newtons, a distance of 0.4 meters, and okay, it reaches a height of 30 meters when I shoot it straight up in the air. All right, so what I'm looking for here, okay, is the mass of the rock. Now, what should I assume the initial height of this rock was? 0. Okay, I have to. They don't tell me otherwise, so I have to assume it is. All right. So force times distance equals, okay, the change in potential energy, right, which is going to be m times g times hf. I'm not going to bother writing the m times g times hi because it equals 0. Well, we're going to say it was measured from where it actually left the slingshot. But you're right. I mean, we could put that in there. Okay. All right. So we're going to manipulate here for what? For mass. Okay, so I'm going to divide both sides by GHF. All right, and plug in our numbers here. So we got 1,400 newtons? 1,500 newtons. Okay, times 0.4 meters, okay, divided by 9.81 times 30, okay, and that should come out to 2 kilograms. Now, okay, Samuel brings up a good point here, okay, about I thought the initial height would be negative 0.4, right? In a case like this, we always want to measure it from the, like, 0 points, okay, so yesterday everything was measured from where the elastic band was not stretched, okay, well the gravitational potential energy also has to be measured from where the rubber band was not stretched. Okay, everyone follow me there? So that's kind of the reasoning on that, just so you don't get confused with it. If you're not told otherwise, you're going to assume, okay, that the initial height of something is 0, because that's typically where we measure potential energy from. Okay, is from a height of 0. Peter? No. It's elastic, right? When I pulled back on the rubber band that makes up the slingshot, I put elastic potential energy into it, okay? But I didn't give it gravitational potential energy. If anything, I took it away, okay? But like I'm saying here, we're only going to measure gravitational potential energy from essentially ground level, right? So we're assuming this was done on the ground. I could only pull it as far as the ground. I can't pull it under the ground unless I dig a hole. Yeah? So we're going to assume that, yeah, that's what we're going to assume. We're not going to assume that I did it from here and I got to know how tall I was. I'm not going to make tricks like that. That would make a question just about tricks and not about how well you know your stuff. Okay? So you got to speak up, I can't hear you. Well, you did. When you went force times distance, that was the elastic potential energy. Okay? Remember, when I do work on a system, I give energy to that system, okay? So if I go 1,500 times 0.4, what do I get? Someone just punched it in real quick. It's my calculator. 600. All right. I did 600 joules of work. That means there's 600 joules of elastic potential energy in the slingshot system. When I release that elastic potential energy turns into kinetic first, right? It increases the speed of the rock that's in the slingshot. Okay? As that rock travels upwards, the kinetic energy turns into gravitational potential energy. But at no point can any part of that system have more than 600 joules of energy, because that's all I put into it when I did the work. Okay? When I pulled back the slingshot and did 600 joules worth of work, I put 600 joules of mechanical energy into that system. What the system does with it is up to the system, but it can never have more or less than 600 joules worth of energy. Okay? Once the rock leaves the slingshot, how much energy does the slingshot have? None. It's done. Okay? It doesn't have any energy. It used it all to do work on the rock. Now the rock has all of it. Okay? The rock's still part of that system, okay? Because it was in the system when I did the work. Follow me there? Okay? Remember, energy can't be created and it can't be destroyed. So once I put it in, it's there. Okay? It can turn into other forms, but it's there. Okay? With me on that? Let me get a rubber band. Okay, so guys, just pay attention here, all right? Number 7, okay, is very much like what we've just done. Cameron. Okay, is very much like what we've just done. Okay, it's a work energy theorem question where we're changing the kinetic energy of the arrow by doing work on the bow. Okay, so I'm going to pull the bow back with 100 newtons worth of force. I'm going to draw it back 0.29 meters, and I want to figure out how much kinetic energy it could give an arrow, okay, and thus how much speed it could impart to the arrow as a result of the work I initially do on it. Right? So the work I do on the bow is going to be equal to the change in kinetic energy of the arrow. All right? Now, when I have drawn back the bow and I'm holding it, how much kinetic energy does the arrow have? None. It's not moving. Right? It's just sitting in the bow. Has no kinetic energy because right now all the energy is potential, and it's in the bow, not the arrow. All right? When I release the bow will exert a force on the arrow. Okay? Through the same distance. That's why it'll be the same amount of energy, be the same force, the same distance. It's going to have the same amount of energy when it leaves the bow. Okay. So force times distance is going to equal the final kinetic energy of the arrow. Right? Because once the bow snaps, the bow won't have any more energy in it, and the arrow will be flying. So I'm solving for VF. So I want to divide both sides by half of M, and then square root. All right, so then I plug in my numbers. Okay, 100 times 0.29 divided by 1.120 times 0.5. All right, when we do that, we should get 22 meters per second. Okay. Does that answer your question, Hannah? All right. Any other ones there, guys? All right, so we got a skydiver here. Okay, so they fly the plane to a height of 1,250 meters. He has a mass of 55 kilograms. How much potential energy does he have? Okay, how do we calculate potential energy? Nope. M times G times H. Do I know M? Do I know G? Do I know H? Just multiply them together. You got 6,700 and, or sorry, you got 674,000. Yeah, that's fine. That's scientific notation, right? 674,000 is 1, 2, 3, 4, 5. Right? Each thing is 10 to the 5, right? Or each thing is 10. Each thing is a factor of 10. 10 to the 1, because it would be 10. 10 to the 2 is 100, right? Follow me there? No, I just always do out of habit because in physics we do that. Okay, so number 11, okay? Number 11 is asking, do you understand the idea that energy can't be created and it can't be destroyed? Okay? If when he jumps out of the plane, he's got that much potential energy, how much kinetic energy will he have when he hits the ground? Just the instant he hits the ground, not after. You're right, after he'll have 0 because he'll do work on the ground and change the ground shape into a Sam-sized crater. Okay? Same amount. Okay? When he jumps out of the plane, all of his energy is potential. But as he falls, it gets converted into kinetic. That's why you speed up as you fall. Okay? Your potential is being turned into kinetic. Your energy is changing from one form to another, and that's why you can do so much work when you hit the ground. And conversely, the ground can do work on you. Not the desirable kind. All right, so this is my energy when I hit the ground, and it's all kinetic. So EK equals 1/2 mv squared. I know what EK is. Sam's mass hasn't changed. Okay, so I divide by half of m and square root, and I'll have v. Okay, so when I plug in those numbers, that's 674,000, okay, divided by half of 55, square rooted, should give me 156.6 meters per second. Okay. Does that make sense to everybody? Okay. We haven't talked about conservation of energy yet, so we're going to talk about tomorrow, but that's the idea. Okay, is that once you give something energy, it's always going to have it. It can be turned into other kinds, but it's always got it. All right, so if that's what we got, okay, when it hits the ground, it'll only have this kind of energy, right? Okay, so I'm solving for that. I know this and this. Okay. Yeah, you got a square root. Yeah? Tomorrow's Thursday, so you have a quiz. It's on this stuff. Okay, it's on Work Energy Theorem, and I'll tweet that later on today. Okay, so make sure that tonight you go over that quiz, look at these solved examples, okay, to help you out with it, right? Or watch the podcast. It's not going to be anything different than what we've been doing in class. Okay, there won't be any surprises. So make sure you go over it. Okay, so you can get 100% on that tomorrow.